Heyo, and welcome back. I know it's been a long time since my last stream. Had all sorts of computer problems, work got annoying, and so finally got all set back up. I'm using Linux now, simply because it's cheaper than Windows, and a lot of the AI and such is based on running on Linux, so we're going to do that for a while and see how it goes. So when we last met, we had our EUP shell running, and by and large doing most of what we wanted it to do. Had our little game of EUP Invaders, which played somewhat like Space Invaders, although right now we don't have it hitting the bad guys yet. And actually the next thing that was a concern to me was being able to count the number of shots fired, the number of hits, and so forth. And since I believe that's probably going to become more than 2 bytes, or 1 byte even, rather, I went ahead and created another library in order to show large numbers. And that is the binary coded decimal library. Now, I did all this a good long time ago, come back into it and start wondering what in the world was I meaning by this? Of course, because I didn't leave enough comments. So what you'll see is, this entire processor, and most processors for that matter, primarily do two things. They move memory from one place to another, and they do math on those values. So let's see, if we get up here to the actual layout of the registers and such, you'll see we basically have 3 general purpose registers. The T register is kind of special because it's used by internal commands as a temporary register to move things around. Then you've got your data pointer, which is 2 bytes, and your stack pointer, instruction pointer, and all these down here. Let's see if I've got that set up. Yeah, there we go. All of these sections down here are part of the sequencing RAM, or the microcode, if you will. And so you probably won't do much with those. But let's see. What we really wanted to get into was showing how we move bytes around in order to do things. So this binary coded string, or binary coded decimal, there's 2 versions. There's the large version and the compact version. And basically what it is we use 1 byte to represent a number from 0 to 9 in decimal, and don't bother with the rest of the values of that byte. Seems a little wasteful. So other versions have packed those to where there's 2 digits into each byte, using the high and low nibble. But that's I'm going to have a few of these numbers laying around, like fire count and hit count, and maybe some sort of score based off of what items I hit in the game. So I don't really need maybe 5 of them. And if I packed it into compact binary coded decimal, that would maybe save 2 dozen bytes. And the number of bytes of code I would need in order to handle that is much larger. So in this case, I'm just going to keep it simple, unpacked binary coded decimal. And so we'll look at how that works here in a second. Let me just get some other things going here. Let's say hi to the chat in case anyone comes by. And let's see. So this binary coded decimal library basically has a max number of 999, 999, and 99. And I probably won't ever use that many, but that seemed like a good basis to go with. So eight bytes. So I mean, if I managed to pack eight digits into 4 bytes, it wouldn't save a whole lot, and it would be much more complex. But basically, this library has 4 functions. Really, only 3 of them exist right now, which is to zero out the string, increment by 1, and to print the string. I haven't had a need for decrement yet because you can't get into negative numbers or counting down in your in the game yet. So let's see. Wanting to show how this works, let's look at the first function, which is the 0 function. So this defines a function named bcd0, and it expects the pointer to those 8 bytes to already be in the DR register, which is this one here, the data register or data pointer register. And so before you call the function, you load that location of the string. And let's look at the test function for this real quick. Here it is, the test. We're going to define a function for test binary coded decimal. Then we're going to create a variable, which is our test function binary coded decimal string, and it is bcd_lib string length long, which over in the bcd_lib we defined that as 8. So C is a constant in my assembler, and D defines a location in ROM. It can be a function, the start of a function, or it can just be a label. Works out to being the same thing in my scheme. So we define it as 8 bytes long. So we've defined our function, we defined our variable. V is for variable in RAM. A is the length, that's the number of bytes we add to the address register to give space for those 8 bytes. And the very first thing we do is halt. And we do that in order to sort of step through this code. In fact, that's the entirety of the code there. So what we do is we load into the DR register the address of TF_BCD, which this is what sets it. This is where we access it and we read it. So like every other string in C, it's the pointer to the first byte. And then we call BCD0. After that, we load up the string that tells the display to go to home and print that string. Then we load the BCD pointer again and we print it. Then we load it one more time and we increment that value. And then we jump, regardless of condition, back to this symbol, which is go here. So you don't want to make the mistake of jumping into a function using this label versus this label, but again, it amounts to the same thing in the assembler. So let's go ahead and see how that works. Let's exit out, restart, restart, run the test function, and you'll see we've hit this halt. So now we can actually sort of single step through and see how each function works. But to begin with, let's go ahead and run it. And you'll see we now have this large number that's continually incrementing. And that's essentially what this entire loop does, right? Initialize it. Initialize it. Go to the home corner of the screen. Load it, print it, increment it, and loop around. So now let's actually take a look at what we're doing in those functions. Get some water here. Now, it hasn't been so long and since I wrote some code. hasn't been so long that I've forgotten what our assembler instructions mean. But the point of writing comments isn't to say what the line does, but rather what's the point, the why of why that line is there. So let's go into BCDlib. We'll take a look first at our BCD0, which blanks out the line. And in reality, in order to have no leading spaces, you see the number grows. Let's go ahead and reset it. And reset was, oh, it wasn't that. Oh, there we go. Reset's F4. All right. F4, and then, well, let's reset it the hard way. There we go. And test. So if we step through, you'll see we've just loaded up into the DR register 0137. 0137 is the start of the location in RAM that we are going to store our string, which is these 8 bytes here. So we're going to jump into the BCD0 function. We're going to load into B, the B register, this guy here. We're going to load the string length from the library. And then we're going to decrement B by 1 because we want to start decrement B by 1, yes, so that it will be, actually the comment's wrong in it. We loaded B that length, which was 8. All right, so we loaded into B 8. Now we're at 7 because we decremented B. This is actually B equals that. And we're going to do the sum of the DR and the B register. And what that's going to do is change our DR pointer from the start of the string to 1 less than the length of the string, which would be the end of the string. Right? So, hit the wrong button. There we go. So now we're going to put 0 into A. And what we're doing is writing the null character at the end of the string first. So we load A with 0 right now. It's 9A. Now it's 0. Now we're going to store indirect, meaning store at the dereference of the DR pointer at this location, a 0, which it's already 0, so it won't be terribly interesting, but we'll do that step. Now we're going to load into A the value 0A, and that is 10 digit in decimal. But what we're using it for is to mean this character doesn't need to be drawn because it's a leading space, or will be possibly be a leading space. We fill all the string with leading space characters, which would be so that we don't print them, right? So first we load that A into A. There we go. Hexadecimal A into register A, to be specific. Then we're going to load into B the constant of the string length again. So B is 8. Now we're going to decrement B so that it's 1 less than 8, right? And it's no longer pointing at the end of the string, it's 1 less than that. Now we're going to decrement the DR pointer so that instead of pointing to this byte, it's pointing to the one right next to it. As you can see it highlighted there. Now we're going to store indirectly whatever value is in the A register. So right now the A register is 0A. We're going to store it in that location. There we did. Now we're going to decrement B. B is the counter for how many times we're going to do this now, right? So we decrement B, it's now 6. And then we're going to jump back up to this label and run through this loop the appropriate number of times until we have zeroed out all of these values. So we're just going to single step through all of that. And as you can see, we've got all of these A's showing up in our string. A means a leading space that doesn't need to be printed. I don't want to print all the leading zeros. Let's see, just about done. There we go. And we return from the 0 function. Go ahead and load into the DR register the pointer to this string. These are all defined in our VT100 assembler, which has functions like set cursor and so on, but that one was the, let's save that before we forget. That one was the, oh, it wasn't there. We're back at this test function. VT home string. So the VT home string amounts to this string escape bracket 7 colon or semicolon 1H, another escape character, and the end of string. And that is just the VT100 codes in order to control where the cursor is here in this display. So back to the test function. We will print that string, which don't see anything about it, but we're actually stepping into the print string function. We can step through and using F7 to jump out of that function. Now we're going to load up the location of the test function BCD string and call BCD print. So now we're into print, and as the comment says, we're going to store the location. And to store the location within the function, we're essentially creating a temporary variable that is at stack pointer +2. So we created a constant to say this is our pointer to our BCD string relative to the stack pointer. And the first two things we do is push onto the stack the D value and then the R value. We do them in that order because we're little Indian. So let's see, store those two. And it's not really obvious because the function happens so quickly, but also the stack is way at the other end of RAM. So we start our stack pointer, as you kind of saw here, our stack pointer grows downward from the top of memory, and our programs and everything else grows upwards from the bottom of memory. And perhaps maybe they don't collide. Hopefully. That's why I don't do recursive functions in embedded very much, because there's an indeterminate amount of stack space you're going to take up. And on these small microcontrollers, it was limited like this. So now we're going to, again, we're going to load A into the register A constant, which was the string length. Let's see if I can, we're not going to need that much. We don't really need to see that part of the display right now. And the flashing is kind of annoying. So we load the constant 8 into A. Then we store on the stack the value of the A register. And that way we now have the stack +1 is the location of the A, the length variable. And the stack +2 is the location of the pointer, the original pointer. And we're storing those on the stack right now so that we can refer back to them. Again, we only have those limited number of registers to deal with or to use, so we have to be judicious about where we put our information. So then we executed this instruction, POE, in our instruction set. Let me go ahead and run back down to the instruction set real quick. I know it's a bit of an eye chart, but POE instruction, it takes the value of the stack pointer, puts it in the DR register, and adds whatever constant is the next byte in ROM. So in this case, the BCD string is 2. So we're going to take the stack pointer, put it in the DR register, and add 2. And if we take a look at our actual simulation, there is our stack pointer was FFF6, and we've added 2 to it, so it's FFF8. Like I said, almost at the very top of RAM. So we did that. Now the intent based on the comments is that we're going to put the byte that's pointed to by the DR register into B. Right? So right now our DR register is way down here, right? And it contains the 3701, which was the pointer to our string earlier, right? So we go ahead and load A from memory. So now that brings it into here. Then we're going to increment the DR register to the next location. Now we're going to load this one directly into the D register of the DR register. So now it's 1. Now it points to some weird location that has nothing in it of interest anyway. But then we're going to move from the R into the R register what was in A, which was the first value we read. So now we have our 0137 location of our string, all of these A's, that we set up earlier. And that's how I'm moving from the DR register into dereferencing the DR register. That kind of, actually, what I'm doing here is I'm doing the equivalent of see this. So the first thing we did here isn't the B dereference. That actually doesn't happen until much later. What we're doing here is we're saying DR equals SP plus the BCD string, which is 2. Well, let's do that. Let's just put this in here for clarity's sake. Now this sequence LAM in increment D, load D from memory, load into R from A. This whole process takes and says let's see how to phrase this. It's essentially, we're saying that the data register is going to equal to the dereference of the data register and 2 bytes. And because the data register is now pointing to the stack, though we're just reading back what we stored up here. So that's what all of these instructions do. Let's give it a space here. Oop. And this instruction loads into B. Let's see, B equals byte from our BCD string. Right? That's what it's supposed to be. And what that does is we've just, have we executed it yet? Let's see. Doesn't look like it because B is still 0. So let's go ahead and execute that line. Now we've taken this A and put it into the B register. And because it's an A, we don't want to print it. But should not have inserted spaces. Let's get rid of this line, because otherwise all the references, the line number references to the program we're running, will have moved by inserting lines. So you end up with a mismatch. So what we want to do is see if that's the byte we read is a hex value A. We want to not print it. So these three lines here is the equivalent of if B not equal 0A, go to, as it were, go to bcd print.show. So if it's not an A character, go show the character. Let's get rid of that. All right. So sure enough, the way we do that is we load the value we're interested in, comparing our B register to, and we load that into A, and then we subtract the two. So if you subtract a value from another value and it's the same value, you end up with 0. And that's the flag we're checking at that next instruction, which is right here. It says jump long if the non-zero flag is set. And our actual flags, showing them here. Did I show the flags? Oh yeah, there they are. So the 0 flag is set, also called the invertedly, it's the non-zero flag. So we've got that. We're going to jump down to show, which is just a couple of lines back, right? Oh no, take that back. It was 0 because that is an A. Therefore, we fall through this jump instruction and we go to the next character. So now what we want to execute is the pointer to the BCD string, add 1 to it, right? And we're going to do that to our local copy that's stored on the stack. So again, with the usual procedure, taking the the value stored at DR, the 37 here, loading that up into A, then loading the next, incrementing the DR, loading the next value, which is the 1, up directly into DR, or the D. And then we load R with what was in A, and that sets up our DR register to point back to our location on the stack. It's currently an A, right? So we're going to increment the DR register, right? Now we're looking at the next A in the list. We're going to load that location into the R register, or load the R into the A register, rather, this 38 into that 38. Load into the B register the value of the D in the DR register. So now we have our 3801 here in AB. We then again do that dereference where we say take the stack pointer, triple F6, add 2 to it. We get triple F8, and that gives us our location that we want to store. What was 0137 now is 0138, stored in A and B. So we store A there, which is the same, or is actually changed to 38, I should say. Then we increment and store our B value. And that's essentially this line right here amounts to this line and the 4 that follow it amount to let's see, this is what do I want to say? It is our pointer to the BCD string that's on the stack equals, let's see, it would be AB, right? There we go. Now, let's see. That, let's see, that is not the increment. This line is actually pointer to BCD string on the stack. That value is being moved into the DR register so that we can do the addition on a 2-byte value. It's the only register we can do addition on 2-byte values, or increment decrement. So the DR is equal to that. That's what these 3, 4, 5 lines do. And then the 6th line is where we actually increment the DR register. This is DR++. Then these two temporarily hold the value of DR so that we can use it again to point to our variable on the stack, and then we store them off. Clear as mud. There's a lot of moving around when you only have one 2-byte pointer register. Let's see. So that, as you see, we've managed to increment from 37 to 38 for the pointer to the next character. And the next thing we want to do is load the address of our increment variable off the stack. So we use the POE instruction again. That loads FFF7 into DR, which is the location of our originally 8, and it will shortly be 7, length of the string. So let's see, we load into B whatever is in memory pointed at by DR. There's our 8 in B now. Then we decrement B to 7, and then we store B back, right? And so this set of instructions is essentially our I minus minus. Next thing we want to do is jump back to the do loop symbol. The do loop symbol back up here. And so we're going to do that time and again until we are exit this function. And really wish I could put temporary breakpoints in. It'd be so much easier. But let's see. I guess we could single step through it a couple more times. But since everything's going to be skipped, it's not very interesting. So let's go ahead and jump out of this function now. All right. So that was our print, and it printed a single 0 because this whole string is 0. Now we're going to increment our binary coded decimal string. So let's step into that. And again, the first thing we do is store our pointer to our BCD string onto the stack. It's called pushing the bytes onto the stack. And since we want to start at the ones position, right, we want to get to the end of the string. to do our increment. So we're going to load our location into the DR register of where we stored the location of the BCD string, and load that value into A, increment, load the next value into D, load that next value into, so now we're back at DR pointing to our string again. And then we're going to load into A the string length, right? String length is 8, so we're going to load that into A, it's a constant. And then we're going to sum A and the DR. So DR will become 0137 plus 8, which is 130,138. And that's pointing at the end of our string. Then we decrement because we don't want to deal with the we don't actually want to deal with the null terminator. So we decrement dr1, and we're going to load into well, we're loading this value back in. R goes into A, D goes into B. Then we load up our location of our variable on the stack again, right? And we're going to store A and then store B, which is the same value. And now our DR pointer is pointing to the second to the last character of the string, our copy of our pointer on the stack, I should say. Well, it's almost there. We actually have to store the B. There we go. So now what we've basically done is we've pointed toward the ones column of the string, skipped to the null, and we are going to, again, this, yeah, we should really put more comments in, huh? So this is the line that is actually making B equal the dereference of our pointer .bcd string. And all of this is doing is taking the BCD string value, which is the address of the string. Let's put it this way, from the stack to the DR register. So I guess if we did this in the C language, it would be the goal of this line is DR is equal to the address of PBCD string. And then we read our character from that address. And remember, we've already moved it to the ones column. So let's do all those steps. Get our DR register pointing at our location for our string pointer that we just stored. Load one value into A, load the next value into B, which apparently they already were because we just used them to store. It's where your compiler can do some optimizations, right? Don't really need to do this again. These 3 lines I don't need to do again because they were just there. The A and B values were already there from earlier on. So here we're going to load D, and now our DR pointer is now pointing again at that last character of the string, which is currently 0. Then we're going to, let's see, right, now we want to read the value from that into B. So we read the B is 0 now. And we're going to increment B because that's the goal, right, is to increment. B is now 1. And now we want to find out whether we've reached the top of the numbers. We're only going to show 0 through 9. So we need to find out whether we incremented to A. And we do that with this, which amounts to an if statement. So if B equals 0x0A, right, we are going to go to BCD increment.c for continue. These are all arbitrary label names, but I guess I could have been more verbose with it. I'm finding myself looking at the OBS studio rather than my screen, but I've basically got copies. Anyway, so let's save that off. Let's see, where are we? We're about to, there we are. So we subtract A from 0, right? And you get 9, I guess. Is that right? Subtract into A. So this is essentially, this instruction amounts to A equals A minus B. So B was 1, A minus B is 9, right? But in any case, it's not 0. You'll see our non-zero flag is set. So because it's not 0, conditional jump will go down here to continue. And we're going to store in the value that's in the DR register what's in the B register. All right, now it went from 0, now it's 1. And we're going to increment out of the stack, or increment the stack pointer to repair it. Basically put it back to where we were so that we can return correctly. There we managed to increment the BCD value. We just incremented the lowest, the ones column. And now we're going to go back and print it. So, yeah, unfortunately I don't have, yeah. All right, well, we'll go to print it. Let's step out of that function for the home. We'll just, should we step into print? I guess we haven't stepped into print yet, have we? Yeah, we did. We did print once. But now if we do print and step out of that function, now we've got our 1. So if we just let this run from this point of view, there we go. You see it increments quite quickly when there's nothing else going on in the loop, right? We're just increment, print, come back here, increment, print, come back here. So that's our binary coded string. Now, it might be interesting to see what happens in the rollover, but I think we would probably want to, let's see, save that. We would probably want to halt. Unfortunately, I can't halt if it's 9, right? But I can cut into this loop. And what do we want to do? Let's put a halt right here before we loop. And in doing so, we can relatively quickly step through until we're at 9, and then we'll walk into the increment function when we're at 9. Sound good? Sounds like it'll take less time. All right. Exit that. BNR builds and runs this whole thing. So there's test. We're at our first halt. And now, every time I hit F5, you can see there's a 0, 1, 2, 3, 4, 5. And we're stopping after we print it, so 6, 7, 8, 9. And now let's start single stepping. There's our home, print that, jump out of the print function. Oh, dang it. We already incremented it. Should have stopped at 8. All right, so we can start this over, but this time we'll start at 8. Stop at 8. All right. Well, odd that it stops there. Not sure what that's about. Anyway, there's 4, 5, 6, 7, 8. Wonder if we're having a display issue. Let's see. That again. Let's see. All of the files are saved, so we're not getting an invalid reference. It's supposed to be shell function 208. I see. What's happening is it's not always coming back to the file that we're interested in when we're halting. Kind of a downside to not having an integrated editor. But anyway, that's where we're actually at, right? So F5, we get to that halt, we're at 0. We're at 1, 2, 3, 4. I think I'm accidentally hitting F5 in the editor. That's might be what's happening. 5, 6, 7, 8. All right, we're at 8. Jump back up there. We can get into printing the string. We just jump out of that. Oops. Did I hit F5? Yes. Should have hit F7. Starting over. What the fun of programming if you can't start over and over? Why is that doing that? Well, let's just delete, or not delete, but close the files we're not as interested in for now. We got the BCD lib and shell test function. Those are the only two we actually care about. 3, 4, 5. Did it again. Seems odd. All right. Now we're at 8. We've actually already incremented it, so it should be 9. So let's single step through that. We go back to printing home. We jump into the print string function. Use F7 to jump out of it. All right. Now we're going to print it, and it should print 9. We'll jump out of that. There we go. We printed 9, right? Now we're about to increment it. So this should be interesting. This is where we're going to change the value from 9 here to 0 and this being 1. You see that? Okay. So that's our binary coded digit. And like I said, we're only using unpacked binary coded decimal. So we're taking up a whole byte just to store values from 0 to 9. Now let's step into the increment. Store off our DR pointer onto the stack. Load that location. Again, DR 0137 was our location at the start of the string. Load A, increment DR, load the D with the location in memory, and then load R with the A that we got from the first byte. And then we're going to load into DR the value from the stack. Now we're looking at the string in ROM, or RAM rather. In the start of the string, there's our 9 at the end. So we're going to add the string length. Right, now we're looking at that, looking at the null terminator of the string. So we decrement DR. Now we're looking at our 9. And we're going to store off that new location back onto the stack. So we load DR into A and B, load the DR with the location of our variable on the stack, and then save off of those two values. All right. Now we're going to grab the pointer to the string again, right? And load that back into the DR register. Now we're looking at our 9, right? Now that we're looking at our 9, we're looking at our 9, we're going to read that, and we're going to see if it is equal to A or not again. So we load our value 9 into B, right? And then we increment it. Now it's A. Now we're going to load the constant A into A. Seems a little redundant. Subtract A from A, we get 0, right? So our not 0 flag is no longer set, right? So we're going to not jump here. We're going to load A with a 0. That's one of the in particular instructions, even though it already is 0 because that's what we did the calculation on, right? We don't necessarily need this instruction, I guess. Again, that's what compilers do for you. But for verbosity, we're load 0 into it, and then we're going to store A where this used to be 9, now it's 0. Now we're going to again get the pointer to our string into the DR register. It looks like we already have done that, but we're doing it now for the purposes of getting to the next character, right? So there we are. We're looking at the 0, the same 0 we were looking at before, so I guess this is kind of redundant code. But we now decrement. We could probably see. How would I? Well, we'll essentially comment it out for now, and we'll see how well it behaves. How's that? Because all we need to do is this decrement, and we should be in the same. Should work the same way because we already had the value up here when we stored A in it, or stored 0 in that location, so it was already set to that. We just needed to decrement. not reload the variable. And see, this is what happens with the C compiler. You'll have an instruction like a pointer to BCD string minus minus, and it won't know necessarily that you're already have loaded that value, and so I should say unoptimized C compiler would just do this. It would load it every time it needed it, even if this previous instruction it was already at that value. The optimizing that happens in your compiler gets rid of those things for you and makes your code that much faster. In this case, we're saving 1, 2, 3, 4, 5 instructions. They're of varying lengths, so half dozen cycles. I don't know. We could figure it out, but it's not that important. Not for this stream, anyway. So we decrement the DR. Now we're looking at this character here that's an A, right? We're going to load that into B, which it already is. Again, it's already B, so we could probably get rid of those two. Although it's not necessarily true. This may not be A the next time we come through, right, as our digits grow. In fact, it's about to be changed. So load that into A. We subtract A from A, we get 0. And if it's not 0, we're going to move on to this location. But since it is 0, we're going to fall through. We're going to load A with 0. Again, we already did a calculation on A being 0, so that's probably redundant. And we're going to store that 0 into this location. So now we went from 0 to 9 in this byte. Now we're going to 0, well, to begin with 0. Then we're going to do the storing of this location, 0, 1, 3D, into A and B. There they are. Again, load up our stack pointer value of the start of the string, right? Oh, we're changing the value here. We're storing where we last were. So we were at 3D before. So store that back in our stack pointer value. And jump back to do. So let's load that up again. And we'll see we're looking at 0, 0, 0, 0. So we load in B, which is 0. Then we increment B to 1. And we are going to compare it to A. It's not equal to A. So we're not going to go down to C. Or we are going to go down to C because it was not equal. And we're going to store B back here. So now we went from 9 to 1, 0. Again, clean up the stack and return. We're at our halt instruction. Come back to our print. So if we just say go from here, this should print 10. Bonus. That seemed like a lot to walk through, but to increment numbers, but that's binary coded decimal for you. So we just do that whole sequence over and over again. The next time through, it's going to detect 0, 0, 0, 1. That's not it, is it? Oh, we already incremented it here. So now it's 1111. So I think if we just, there we go, 1 2 1 3 1 4 1 5 1 6 1 7 1 8 1 9 2 0. I'm just thinking of extra features I need to add. I definitely need to have a way to set a breakpoint at a particular address. And that would be, when the instruction pointer is at this particular address, halt by default. And anyway, this little simple microcontroller doesn't have those kinds of features. So let's see. We've got our 1-9s. So we've got our binary coded decimal string. We can increment that string. So now what we want to do is make that, say, a fired count, right? Number of things fired in our game. So let's go look in our game for where we hit the fire button. And we'll create one of these values, initialize it at the top of the game, and then we will, well, first off, we made those changes earlier. Let's go ahead and see if that screws anything up. Eight, 9, 10, 20. Doesn't look like it. Looks like we were good. So these 3 lines or so that I commented out of increment, 4 lines, we just save some instructions. Ain't that lovely? So again, let's go back to the game. Well, we can exit out of here. Open up programs, game libs, EUP invaders, and there's the assets and the code. So just to give you an idea of the assets, these are all the character codes used to draw the blocks, the shields, when the blocks disintegrate. That's interesting. I guess I hadn't put that in yet. The blocks were supposed to go from solid to less and less solid and then disappear. Anyway, right now they just disappear. So let's see. Here's our little good guy character, etc. There's what happens when something explodes. And here's our shots fired and shots on target that we originally used. And, I guess it is 2 bytes. That's 65,000 shots. I don't think we're going to go through a game using more than that. But let's go ahead and create another one, which will be, let's see, EUP invaders. Shots BCD. And then we're going to add to that address our BCD lib constant of string length, which, if we're not going to get to 65,000 shots, we're not going to get to 9 bajillion either. But we're doing it for the exercise mostly. So there we go. We'll add the 8 bytes to that. And then let's just get a copy of this. And so we're looking for where we incremented shots fired and where we draw the game. So that's our assets and variables. And this is the code itself. Our draw bad guys function. Check for collision. Check for no collision. and then move the guys right and left. So we want to find where we fired our shot. Let's see, draw bad guys. Here's our main loop. All right. There we go. There's where we load our shots fired, and we call the function to increment a short value. So at that same place, we want to load into DR register our shots fired BCD and call, what was it called? BCD increment, I believe. Yeah, BCD increment. Back over here. There we go. That's where we increment it. Now we need to initialize it and print it. So here's our main loop. Draw good guys, draw bad guys, draw bullets. And this is done for every game tick. We're actually slowing it down here. So I think, if I remember right, every game tick has a clear screen between it. So I guess we can just right up here, we're going to load our BCD string into the DR register and call BCD print, if that is what it's called. Yeah, BCD PNT. And that should put it in the right place all the time. But if you remember, we have to initialize the BCD string. So we're going to actually just grab this whole line. So we're going to need to do that. And we need to do it before the main loop. So let's see, where is the main loop function called? It is a function, right? Yeah, main loop. So let's find where that's called. There we go. See, we drew the banner. So knit the shots fired. And it was called BCD 0, actually. BCD 0, there we go. So that should add it to it and should print in the top left corner. Should. Just make sure we save everything. Rebuild, rerun. Stop the EUP invaders. Looks problematic. Oh, there's our O right there. So let's start firing some shots. Well, that's the problem with that, eh? Ooh, our shot count changes every time, and I bet you it'll change with the column too. Yay! All right. Well, that's probably not the right place to put it, is it? And we want it to be at the top corner every time anyway. So let's see. Where do we want to print it? We'll have to look at the game loop, see what's a better place to print it. All right. So it's got to be in the main loop somewhere. Does the main loop not clear the screen? I thought it did. Main loop. Oh, you know, it doesn't clear the screen every time. That's right. And we weren't telling it where to write that string. So maybe we should do it right after, because this loop is also doing all of the bullet movements, right? Right, here's the bullet row, good guy position, and so forth. We'll play the bullet sound. Well, all of these are calling set cursor position before they happen. And so that's probably what we need to do as well before we print it. And let's see. So right after that, or right before, or right after the sleep, but right before we draw the shots fired, we need to set the cursor position. And the VT set cursor position is in the VT100 lib. And the standard libs, nope, not standard libs, display libs. VT100 assembly, VT set cursor position. That's the actual string for setting the cursor position. This is the function. And A and B is column and row. So 0, 0 is a good enough place for now. So before we call set cursor position, we need to call, let's load A with 0, load B with 0, and then call the cursor position, and then load up the printing of the thing. So that ought to do it. That'll fix her. Right. I don't see my 0 now. Oh, you know what I'm doing? It's not 0, 0. This isn't 0, 0. That's 0, 0. And it's getting rewritten all the time. And I think I had a variable for that, if I remember right. Row. Is there row and column? Column and row. Column and row. I thought I was adjusting that automatically. Anyway, let's see. 1, 2, or 0, 1, 2, 3, 4, 5, 6. So let's put it at 6 and see what that does. So we want to load B with a constant of 6. So now it's row 0, column 0, row 6. I'm not even sure if it's 0 or 1 based. I don't remember. But it's faster to find out by trying than it is by searching through all the code. Rebuild. Ah, almost. See, that's where I thought. I thought I had added the 6 automatically. Anyway, let's see if we get our increment the way we expect it. Ooh, interesting. An effect I wasn't looking for, but yeah, no, it changes color every time you Right now it's not actually going by when you collide with anything. It's based off of firing again when the first one is at the right height. Alright, this may be a little annoying, but stick with me. Looks good. The blinking effect is a little happy programming accident, but maybe we don't want it there though. Maybe we want it like more or less centered. So this is a 80 column screen, so it'd be, let's just put it at say 44. And instead of 6, it looks like it's 6 from the top, which must have been one off. Gotta be a one off error somewhere. See what happens if we make it 1 and 44. Although I believe that is hex 44, not decimal. Hoody doody do. Hex versus decimal. What fun. Print the ASCII table. 44. Nah, that's not helpful. I should probably do a function that converts from hex to decimal for me. But let's just ask the phone. Why not? It's got a little calculator on it. Let's see. We want it to be 44. If we divide that by 16, we get 2 3/4. So the first digit's going to be 2, and then 3/4 of 16. So 16 times 0.75 gives us 12. So the first digit's 2, hex digit is 2. Oh, now I'm wondering, did I? So, I don't know, I've been making various improvements to the assembler over the time. Let's just see if it doesn't burp. Otherwise, it'll be 2B, I think. C, 2C. But maybe I'll take a constant and not have to have it in hex. I don't remember. I think so. Let's just see if the assembler burps on it. Didn't burp. Is it in the right place though? Oh, yeah. Roughly the right place. Ah, now I remember. On the one hand, there's the shots fired, right? Probably going to be less than 65,535 shots per game. But I guess it could be more. But it was because of the scores. Because if you hit one thing, it's plus 10, another thing, it's plus 15, another thing, it's plus 25. And that could very easily get to beyond 65K. That's what I started doing all this binary coded decimal code for. Let's see. Well, on the plus side, I did add to the assembler the ability to take constants as decimal or hex. Kind of forgot that I had done that. Alrighty. We have been going for about an hour and a half. Let's see. I guess one other thing I could explain real quick, maybe not. So all of these special characters, all these bar characters, box drawing stuff, it was all based. Oh yeah, let's do that. So these characters were all based on the old ASCII extended format that was standard in DOS forever until they came up with Unicode. So Unicode has a different encoding standard. UTF-8 is used by default. So when I use those special characters, UTF-8 didn't know what I was saying, and it drew all sorts of garbage. So I had forced it more or less to be compatible by going into preferences here and making the compatibility something other than UTF-8, and that almost worked. But where it failed was with the card suits. And, you know, if I'm going to have some card games in here, I need those card suit characters. So let's go back to the test function, shell test function. And right here we have test BCD, but before that we were playing a sort of test of games of a card deck, actually. So we will comment out our call to the BCD test. And now when we run test in here, we print our deck of cards. And conveniently, it has the card suits. Also, I'm working out some larger LED numbers. So I probably could have done this without all the beeping, but in any case, these are my initial sort of big LED numbers. And the box drawing characters make it somewhat convenient to draw serif fonts. So I might add some serif fonts to these guys. In any case, so the reason I had to switch this over was in order to get what is referred to as code page 467. And we will bring that up in here. So this is the code for the emulation itself. And you'll see this character B3 wouldn't print properly in the UTF-8 encoding. So I created this table. And what this table does is for every possible 0 to 255 value of the old bytes, it now uses the encoded UTF or Unicode version of those characters. And so it all works in the modern terminals. I believe this will work on Windows as well, because whenever I run this in the debugger, this was another intro that I used to use. Let's stop and restart. Restart. So this is actually, I guess it's not Windows Terminal, is it? It's all on Linux, but it's inside VS Code. So I think it will behave. And there's some examples of the other letters I was playing with. Let's see. So yeah, essentially what I had to do was throughout my printfs in the emulation. Boy, that's slow. I had to replace it with a printf for code page 437. And this kind of, some of them I don't have to do that, right? This string doesn't have any special characters in it. I can just use standard printf. The code page 437, let's go to that definition. So it behaves like a printf, takes the var args, and then does a vs printf into a temp string, then runs through those strings, converting unsigned characters to, or signed characters to unsigned characters, which is kind of annoying to have to do, but since a negative some number is going to go blow up the table. But anyway, so we look through it in character by character. So this is why I kind of took a hit. I'm not quite doing 26. 26 megahertz. I think I'm doing, 22-ish megahertz now when it's sitting still. Every time I play a sound, the delay is discounted from the cycle count. So anytime you see a bunch of sounds, in fact, I think that's why it's dropping so much, because if I do that, you'll see our speed drops to like 140, 136 kilohertz, not even megahertz. So I think that's because I'm playing the sound, and the time it takes to play the sound is not part of the tick count. So that's easy enough to test. Exit out, and I'm sure y'all will all be happy if I get rid of the stupid test sound, beeping sound anyway. So where is our sound function here? Again, no comments. Well, I know what makes the sound, and that is out of writing a value write a value out to port 2, a constant value. So if I comment that guy out, let's search for him again just in case. No, okay, good. So that should get rid of the beeps, and we're saved. Run it again. Wow, that's super fast. And we're not trashing our megahertz frame rate there. Oh, went too far over for the 9. I think these are just hex digits, 0 through F. And where are we printing those? There's our red on black. There's our call to print LED. Set cursor position. Cursor position of 20. Does that look like 20? Might be. Let's set this back down to say maybe like just, I don't know. Let's set it to 4. See if that fixes it. Oh. Well, that was not the value you wanted to change, was it? Undo is your friend. Was it this 12 then? Yeah, because A is the column, B is the row. Let's move that to 2. See if that makes the change we're expecting. Yes, that makes the change. 6, 7, 8, 9. That's supposed to be A, B, C, D, E, F. I wonder if I can close the gap between them as well. And since we found that out, we should put a comment to that effect, right? Yeah. LED prints. Starting column. Row of LED prints. And then, let's see. Then we print the LED, we load the TF.I, we load it into A, increment A, store A. So that's just an increment counter. Test function.loop. So this function docRC function. It's a horrible name for a function, isn't it? Let's see. This is the draw card sound, and then we drew. Oh, let's see. Where is docRC called? Right there. tf.column load A would be add 6. So that's adding 6 each time to a value. I believe that is the gap. Now, characters are 3 wide, so it look like we're doing 3 and then 3. Let's just move this to 4. If I'm right, if my intuition and vague memory is correct, that is going to be the gap, because we're summing it to a value of the column here and then storing it back each time. So let's see. I think this is the gap between LEDs. Let's go ahead and test it right quick. Nope. Clearly it had to do with the cards instead. That was not the thought. If that's the starting row and column, print LED. Well, it is definitely going to have to be wherever we do this. So let's find if we do that. Nope, we only do it once. So we must be, our cursor must be moving some other time. Let's go ahead. There's a set cursor position. Let's see. Was I trying to be cute here? This looks like I'm trying to be cute. Starting column. We load the DR that, and we load into B, the increment, and then we shift left B several times and add B to A. Interesting. An odd way of doing it for me. So let's see. That is the starting column. And then the number 1, 2, 3, 4. What a strange way of doing it. This should be the number we're going to print. Alright, we load that value into B. And then we shift left 1, 2, 3 times. And then add that to A. Let's see what this is. Let's go ahead and I'm going to put a halt here. And save, exit, rebuild, rerun. Alright. So we printed out the deck, right? Now we are going to load the constant 2 into A, which it is. Correct. Now we're going to load into the DR register the pointer to our I. Right, it's currently 1. Then we're going to load B from memory. So we're going to load that 1 into B. We're going to shift B left 1, 2, 3 times. We're going to sum those two. That gives us A. I don't know why I didn't just add 5 or something. Seems like a weird way of doing it. Why would I do that? What was I thinking when I decided to shift left the value instead? Very strange. Oh, because it's from this leftmost corner. So each time we're doing it not the same constant amount, because otherwise we would just, I see what the logic was. There's our 1. Waiting on a character. Now, if we read that in, we're now reading 2. If we shift that left 3 times, we get 10. Sum that to 12. That, maybe I just don't need to shift it left 3 times. Let's see what happens if we only shift it left twice. It's a way of multiplying. That's what it was. Where shift left is essentially multiply by 2. So I'm multiplying the index by 4. I was multiplying it by 8 in order to find the position here, but that seems a bit excessive. So let's just do it by 4 instead of 8. Hopefully they won't run into each other. Oh. There we go. We can get rid of that halt function now. And then load B. Multiply B by 4 via shifts. Previously 8. That can go away. That 4 is awful big. And now we've got them all on screen. Yay! And it only took me, I don't know how long to figure out where I was when I left off. So, not a big fan of that version of LEDs. I mean, they kind of work. I could probably get away with just vertical bar and column, or hell, I might just switch over to dot matrix 3x5. And these are 3 anyway, right? So, like, if we look at the, what was that called? Big LED. I think that was the name of it. Yeah, big LED. So these are the character maps, and this is the character table. And then this is the new line, which essentially is an escape code to print these 3 characters and then go down 1 and back 3. So it's actually, there's the 3 back and 1 down. Kind of odd that that's the. Anyway, VT100 codes are what they are and have been for a long time. So anyway, we define our LED table, and then we define the entry to the first table, which is defined here, the first for the 0, and then that is consistent of several literals, which are 3 strings of 3 characters each. So if we wanted to make this dot matrix, though, they would be 3x5. So they would be somewhat taller, but they'd probably look better. So, I don't know. We'll fiddle with it. Maybe we'll do dot matrix next time. Well, thanks for, let me switch over here. Thanks for joining me on this adventure back in time to my vague memory of what I had done the last time. And hope you got to experience some of what it's like to come upon a code base that you vaguely remember and then have to decipher it from the source code without comments. And so, like I said, add the comments to the lines as you go, and you won't have to do this. Just comment why you're doing a thing and not necessarily what exactly it's doing, because anyone can read code, even if it's assembly code. So anyway, that's about it for now. See you next time.